All right, today's lesson 4.2 in your algebra book, we're going to be looking at horizontal and vertical lines, what their equations look like, and then kind of doing some practical application with them. So the big idea today, every horizontal line has an equation of the form y equals something. K in this case represents a number. And every vertical line, so vertical, has a line x equals, or the equation x equals some number, h. So let's make sure we know the difference between vertical and horizontal. When you look out, watch a sunset, it sets on the horizon. That's how I always remember it. So horizontal, like horizon, goes side to side, like if you're watching a sunset. And vertical, anytime you talk about sports, and you talk about somebody's vertical, it's how high they can jump. Okay, so the equation of a vertical line is x equals h. Again, vertical, straight up and straight down, and this is parallel to the y-axis. So it's not going to hit the y-axis, it's parallel to the y-axis. And again, h just represents a number. So an example, x equals 2, that's the equation of a line that's going to go straight up and down, and it's going to hit the x-axis at 2. So the equation of a horizontal line, these always say y equals one single number. Okay, these go side to side. They look like the x-axis, but if you look at this graph, x-axis goes side to side. Horizontal, it's going to be a line that's above it or below it, but runs parallel to it. So parallel to the x-axis. And an example, y equals -3. So it's going to say either x equals a number or y equals a number. So you're not going to have an x and a y in the same equation. That's what happens when you have a vertical line or you have a horizontal line. It's just x equals a number or y equals a number. So as we move down to example 1, we're going to graph each of the following on this coordinate plane. So starting with x equals 4. So if we go back up here, this is going to be a vertical line. Okay, it's going to look like this. So if it says x equals, it actually looks like the y-axis. It's parallel to the y-axis. It hits the x-axis at 4. And that's how I remember it. When I see these, y equals something, x equals something, just a single number, I know right away it's either going to be side to side, horizontal, or straight up and down, vertical. But it's easy to mix these up and draw the x equals horizontally and draw the y equals vertically and get them mixed up. So the way I remember it is, this is telling me that x equals 4. It has to hit the x-axis at 4. So if I come over here, I know that x equals 4 is going to hit the x-axis at 4. And it's going to go straight up and down, continue on past the graph, both directions. So if I label this, this is the line x equals 4. Anywhere I go on this line, if you notice, the y value, if I took coordinates, is changing. It gets higher up here, the y value gets lower down here, but what never changes about the x, it's always 4. So even up here, we're at 4, 4. Down here, we're at 4, -2, or 4, -4. The x value never changes. So if we come over to y equals -3, if it says y equals, it's going to run parallel to the x-axis, and it hits the y-axis at -3. So if you go to the y-axis and you find -3, it's going to be the line that always has a y value of -3 and runs parallel to the x-axis. Okay, so y equals looks like this, x equals looks like this. They hit the axis that the variable represents in our equation. So going back to x equals -2. X equals runs parallel to the y-axis. It's the x-axis at -2. So again, find your x-axis. It's going to hit at -2, and it's going to always have a value of 2 for x. The y value goes up and down, but it's always x equals -2. And even if there's a decimal, we can still graph this. So y equals a number is going to go straight side to side. And it's going to hit the y-axis at 1.5. So if we go to the y-axis, 1.5 is going to be directly between 1 and 2. And this is going to be a line that runs parallel to the x-axis. Never hits it, only hits the y-axis at 1.5. So this is y equals 1.5. So that's what these look like on a graph. Whatever variable you see in the equation, that's the axis it hits. And it's actually going to look like the opposite axis. So if it says x equals 4, it looks like the y-axis. It's parallel to the y-axis, but it hits whatever it says. It hits the x-axis. Okay, so if we slide down, let's just kind of do the opposite direction. We're going to give an equation for each of the lines that we see right here. So let's start with this one going up and down here. So it's vertical. Think about which axis it hits. It hits the x-axis. So this is going to say x equals, and it's just whatever value it hits, 3. So even if I go up here, the y value has changed to 3 or 2 or 1. The x value is always 3. Let's go down to this one. Okay, looks like an x-axis, runs parallel to an x-axis, hits the y-axis, so it's y equals whatever it hits, and that's -5. Pretty simple. And we do have a shaded line here, and it's sitting right on the axis. It basically is the same line as the x-axis. We can write an equation for it. Okay, so this is a special case where, yes, it does hit the x-axis. It is the x-axis. Okay, but if you see it's running vertically, that makes it a y equals. As I go left on this, the x changes. As I go right on this, the x changes. What never changes is the y. The y value is always, this is 1, 0, 2, 0, -2, 0, -5, 0. The y value is always 0. So that is the line y equals 0. And if you wanted to write an equation for the y-axis, that would be x equals 0. All right, flip it over. So the graph at the right gives the amount of domestic catch for human food in U.S. fisheries in the years 1980 to 2003 in billions of pounds. Okay, so obviously they didn't catch just over 3 pounds of fish. It was just over 3 billion pounds of fish, according to this administration. So notice there's a horizontal line on the graph, and this shows the mean catch. Remember, mean is the average. So if we added up all of these years and divided by how many there were and found out on average how many did they get, what's their test average, what's the average? Okay, it's somewhere in here, about 6.5 billion per year. You had a couple that were lower, most of them were higher, but the average was about 6.5. So which year had the least absolute deviation? So a lot of people would see least and just go up, the least one's right here, but that's not what it's asking. Which year had the least absolute deviation? So what does that mean? We talked about that. Absolute deviation has to do with how far away it is from the average. So the least absolute deviation is going to be the one that's closest to the mean, or closest to the average. So as I take a look, the one that has the least absolute deviation, deviation means fluctuation, kind of how far it is. So the least far looks like it's this one over here. So if you follow that down, that's the year 2000. Okay, and let's write a little statement so we can look back at this. Because it's the closest to the line. Well, what line is this? That's the y-axis. Y equals, now they told you it's 6.48, so it looks like 6.5, but they actually told you it's 6.48. So we can use that number, 6.48. So this is the line, y equals 6.48. The least absolute deviation, so it's the closest to the average, is the year 2000. It's closest to that line. So what does this actually mean regarding the amount of fish that were caught in relation to the mean? So the mean is the average, if this is closest to the line. Okay, the catch in 2000 in 2000 was the closest catch to the average. So on average, every year, it's about 6.5 billion pounds caught. And in the year 2000, just under 7. Out of all the years that we have in this graph, that's the closest to the average. So which year had the greatest absolute deviation? Again, absolute deviation, how far off it is from the average. So the greatest would be the farthest away from the line. So that looks like this year right here. And if I had to guess, that looks like 85, because 86 would be in the middle. 87 would be closer here. So this would be 85. So first of all, the greatest absolute deviation is the furthest from the mean. And so 1985 has the greatest absolute deviation because it's the farthest from the line. Y equals 6.48. So if we considered all of this data again, but without the years 1980 and 85. So if you take a look, those are these two low ones. Those were the years that are most different from the rest. If we took these out and we just considered the rest of the data, that's what it's saying. Would the mean catch, so the average, which is this line, would it be bigger or smaller? So we're averaging all these out. Think about if you take out your two lowest test scores, is your test average going to go up or is it going to go down? Well, clearly, if we take out these low ones and we just average these, this line's going to shift up right in between all of these. It's actually kind of funny that it's not between all these because that's what the average normally looks like. But these two dots have brought that line down. So would the mean catch, be bigger or smaller? Which one? Okay, if we took out the two smallest ones, obviously the mean or the average would be bigger. Why? Because 1980 and 1985 are dragging down the mean. You have those two really low test scores, they're dragging down your test average. If you get rid of those two scores, your test average goes up, the mean goes up.